Good morning, and welcome to the Linux Security Summit. I'm Smalley, and today I'll be talking to you about namespaces for SELinux, or bringing the full power of SELinux within your Linux containers. Today, SELinux enables you to define and enforce a single system-wide security policy over all processes and objects on a given Linux system. But what it doesn't provide today is a way for container operating systems to make use of SELinux themselves. From within a container operating system, SELinux typically appears as being disabled, even if it's enabled on the host operating system, in order to prevent the container from attempting to load policy or setting security labels that might be in conflict with the host's security policy. From the host's point of view, if it's using SELinux, it typically treats the container as running with a single security label. That is, all processes within the container have one label, and all of the files associated with the container are typically assigned a single label through a context mount option. This is useful for enforcing separation between containers and protecting the host operating system from breakouts by the container, but doesn't allow for any kind of fine-grained protections within the container itself. Further, running a system like Android, where SELinux is mandatory within a container, requires a custom kernel and a custom policy typically. Further, for developers, testing with SELinux requires creating entire virtual machines, not just containers, in order to be able to exercise with SELinux being applied as it would be on a host operating system. This reduces usability for both developers and users, impeding wider adoption and use of SELinux in container native workloads. While the LSM stacking work is advancing the ability to combine SELinux with other security modules simultaneously, it doesn't directly provide any namespacing capability for SELinux or other security modules, leaving that up to the individual security module designers to solve. Ultimately, if both the namespacing work and the LSM stacking work are fully successful, one would be able to apply SELinux to one container while applying a different security module to a different container. So what are some use cases for SELinux namespaces? First, one might want to run something like a Fedora container with SELinux fully enforcing and applied to the individual processes within the container on a Red Hat host operating system itself with its own SELinux policy being applied to its processes. One might also want to be able to run different versions of Fedora or Red Hat or other distributions in different containers on a single host operating system. Or might want to run something like Azure Linux on a Red Hat host, or vice versa. Going even farther afield, ultimately it would be helpful if users could run SELinux enabled containers even on host operating systems that do not themselves enable or use SELinux, like Ubuntu or Debian. An even farther stretch goal is the use case of running Android within a container on a host operating system that either enables SELinux or doesn't use it. In the case where the host does use SELinux, this is even more challenging because Android has a completely different SELinux policy and set of file labels with no relationship to that used by Linux distributions. In order to meet these use cases, we have both functional and security requirements, which sometimes conflict with each other. Ultimately, we want to maximize compatibility for running relatively stock Linux distributions or Android containers, while at the same time preventing escape from the container through the use of the SELinux namespaces. Also, in order to be acceptable, SELinux namespaces must not impose any significant overhead on existing users who aren't leveraging them, and in the case where they are being leveraged, must impose minimal overhead to permit scalable use. While the SELinux namespace work itself has only been ongoing for the past 7 to 8 years, work on the notion of nested security servers or nested policies goes all the way back to the early 90s, where work was being done in a research predecessor to SELinux called Flask. Also, in the early days of SELinux, support was developed for hierarchical types and roles, which provided a way of defining nested policies within a single policy. But these still ultimately boil down to a single monolithic kernel policy and didn't offer the ability to associate them with specific containers. Chrome OS encountered this challenge quite some time ago when it began to add support for Android containers running on Chrome OS. And their solution consisted of a custom out-of-tree kernel patch and policy to allow them to support their particular use case. But this was never upstreamed or generalized. It wasn't until 2017 that the first set of SELinux namespace patches were first posted to the SELinux mailing list for discussion. This led to further work contributed by James Morris, which was presented at LCA back in 2018. But there were a number of thorny technical challenges associated with bringing the namespace support to mainline, and thus progress stalled until Paul Moore restarted discussions in 2023 and suggested a different approach to the problem, which ultimately led to a breakthrough when I restarted implementation work in 2024, enabling us to reach the point where today, with the SELinux namespace patches, it's possible to boot a SELinux enforcing container on a host operating system. So with SELinux namespaces, each namespace has its own policy, access vector cache, enforcing mode, and other SELinux parameters that can be independently loaded and set. This in turn requires a per namespace SELinux FS instance, which provides access to the policy, enforcing mode, and other parameters to user space. While each namespace has its own independent policy and parameters to provide security, each namespace needs to be confined by the ancestor policies all the way up through and including the initial SELinux namespace, which would be the one controlled by the host operating system. While there's not a direct relationship between SELinux namespaces and the other existing Linux namespaces, there are certain aspects that need to be understood. First, with respect to the user namespace, which supports namespacing of UIDs and capabilities, it was decided to keep the SELinux namespace orthogonal to the user namespace. This allows maximal flexibility in the ability to combine user namespaces with SELinux namespaces or to use them independently of one another. The mount namespace typically is needed in order to set up a separate SELinux FS mount in order to run a stock SELinux user space, which will be looking for the SELinux FS instance mounted there. In the case where you're using SELinux netlink sockets, it's also necessary to have a separate network namespace. However, modern SELinux user space with modern kernels has pivoted from using the netlink SELinux sockets to using the SELinux status page instead as a more efficient way of getting notifications of policy reloads and enforcing mode changes. Consequently, when using modern SELinux user space and kernels, you don't actually need a separate network namespace in order to use an SELinux namespace. This is a depiction of SELinux namespaces and their relationships to each other, to the policy, the access vector cache, and an SELinux FS instance. As you can see, there's an initial SELinux namespace and one or more child namespaces depicted here. And of course, it's possible to continue nesting further below the child namespaces to a depth controlled by a particular limit. Each namespace has its own policy, access vector cache, and enforcing mode, likewise depicted. And for each namespace, there is a separate SELinux FS instance, which provides a view of that policy, access vector cache and enforcing mode. This diagram does not show the corresponding mount namespace into which the SELinux FS is mounted, nor does it show a separate network namespace, which could be used if using SELinux netlink sockets. In order to support namespaces, it's also necessary to namespace the security labels associated with processes. Consequently, the design for SELinux namespaces enables per namespace security labels for each process or task, where each process has a label in the current SELinux namespace and in each ancestor namespace. Having per namespace security labels is necessary to support fine-grained process labeling intra-container, while still presenting to the host a consistent view with its own policy. With this support, a process only sees the label associated with its own namespace, while other processes can only see the label associated with their namespace. While it would also be ideal to support per namespace object security labels, and this was in fact the original design and early prototyping approach, it ran into a number of thorny technical challenges associated with taking the single LSM security blob for each object and multiplexing it across different namespaces, particularly since an object might be accessed from a new namespace at any point in time, potentially from LSM hooks, which cannot block or perform operations required to initialize one. As a result of these complications, it was decided, based on the discussions back in 2023, to instead simply support a single security label for each object, at least for now, and this allowed forward progress to be made. However, ultimately, we anticipate future extensions to support per namespace context-like mounts to enable similar schemes that are currently applied in systems like OpenShift or Podman, as well as potentially supporting label mappings similar to the UID and GID mappings supported by the user namespace to provide a richer set of primitives for SELinux namespaces. This diagram depicts process labeling, where each process has its own credential structure, which references, through the security blob, a namespace and a label in that namespace. And each credential also references the credential in its parent namespace, so that from a given LSM hook, we can obtain the appropriate label to use based on the namespace in view. In addition to dealing with security labeling issues for the SELinux namespaces, we also had to resolve how to handle security IDs, which are small integer handles to security labels. In the original design, the existing SELinux SIDs, which are ultimately mapped to per policy context structures, were leveraged. This, however, ran up against a number of challenges due to the fact that the kernel actually caches these security identifiers outside of the LSM framework and later passes them back in at points where the particular SELinux namespace that originally created them may no longer be accessible. Consequently, it was ultimately decided after the redesign conversations last year to introduce global security IDs or SIDs and make use of them at the SELinux hook function layer and in its security blobs and LSM interfaces. This global SID mapping maps these global security IDs, which are the only security IDs exposed outside of SELinux, to and from the security context strings, similar to how SMAC maintains a known label mapping with its security IDs. It was possible to wrap the security server interfaces within SELinux to map these global SIDs transparently down to the per policy constructs needed to perform actual decisions. In addition to dealing with labeling, it was also necessary to deal with the permission checks within SELinux to support SELinux namespaces. These were extended to check not only against the current SELinux namespace and its policy, but also to check against all ancestor namespaces with their policies. Further, not only is it necessary to check against each namespace, but also to use the appropriate process label when performing the check in each namespace, walking up the tree of labels maintained from the credential structure. If the target of a check is a process, then it's also necessary to use the appropriate label for that process from the same namespace in which the check is taking place. For checks that occur outside of process context, it's necessary to use a suitable proxy in order to obtain the appropriate label. This requires caching namespace pointers in related objects, such as sockets and open files, by extending the security blobs associated with those objects. If there's no suitable proxy at all, then ultimately it's necessary to fall back to using the initial SELinux namespace defined by the host operating system. This is rarely needed, however, and only really applies for cases such as packet forwarding checks, where there's no other namespace information available. In some cases, it's not necessary to check against all of the ancestor SELinux namespaces. For example, an operation that only affects the current namespace and isn't visible outside of it can simply be checked against the current SELinux namespace. This, for example, is necessary for SELinux FS operations so that we can allow processes within a container to perform operations on their own SELinux FS instance without needing to allow them to touch any other namespaces SELinux FS. Similarly, label transitions, since the labels are namespaced, can be checked localized to the current namespace and don't require walking up the ancestor namespace. This diagram depicts namespace-aware permission checking, starting from the current namespace using the label in that namespace and iterating up through the parent link until ultimately we reach the initial SELinux namespace defined by the host operating system. If permission is denied by any of the namespaces, then we will ultimately return an access denied. Otherwise, we can return access allowed with the combined result from the computations. In order to prevent resource exhaustion through the SELinux namespaces, it was necessary to introduce a set of namespace limits similar to those defined for other Linux namespaces. For SELinux, we defined two limits: a maximum number of SELinux namespaces, which controls the total number of SELinux namespaces that can exist at any given time, set via both the kernel configuration option for a default value, similar to that of other Linux namespaces, but also tunable using SELinux FS, but only from the initial SELinux namespace, so that child namespaces cannot change the limit that's being imposed. You can set that limit to 0 or 1 to disable creating any child namespaces at all if you don't want to make use of the functionality. There's also a separate limit introduced for SELinux, the maximum depth for SELinux namespaces. While there's a similar limit for user namespaces, it's currently hard-coded in the kernel. For SELinux, we decided instead to make it a value that can be set initially using the kernel's configuration, similarly limited to a depth of 32, like user namespaces, but also tunable using SELinux FS, again, only settable from the initial SELinux namespace, so it can't be escaped from any child namespaces. If you wanted to set up a host so that containers launched by the host could have their own SELinux namespace, but couldn't further nest those namespaces, you could set this limit to 1 in order to enforce that guarantee. The next sequence of diagrams shows the process of unsharing the SELinux namespace. First, a process would invoke an API to unshare its SELinux namespace. Prior to unsharing, it has a credential structure with an associated SELinux namespace and a label. And that namespace has its own policy, access vector cache, and enforcing mode, and an SELinux FS instance that allows access to it. The unshare operation creates a new credential structure for the process with a new SELinux namespace. The new credential is assigned the init SID, or label associated with the first process in a new SELinux namespace, and also starts off in the same state as a freshly booted SELinux system before init performs any initialization. That is, it has no policy loaded yet, and it starts in permissive mode. The process can then continue on to perform SELinux initialization, or it can simply exec systemd or another init program and allow it to perform the typical SELinux initializations sequence, mounting a new SELinux FS instance, which will create that new instance referencing the new namespace. It can then load a policy and set enforcing mode, at which point the child namespace is fully set up and will begin to be applied to processes within that namespace while still being confined by the parent. In order to implement SELinux namespaces, it was first necessary to encapsulate and explicitly pass a reference to the global SELinux state, which prior to the beginning of this work back in 2017 was scattered across multiple different source code files and structures. In order to support this encapsulation and explicit passing, a new SELinux state structure was introduced. And this state structure was upstreamed actually as early as 2018 and later refactored during some work that was done to make SELinux policy reloads fully atomic. However, the passing of the SELinux state structure to all of the necessary functions was reverted in 2023 based on feedback from Linus, who was concerned about overhead being imposed when there wasn't yet support for SELinux namespaces fully upstream. That support has been restored in my working SELinux NS branch of my SELinux kernel fork, and then further built upon to support dynamically instantiating these state structures per SELinux namespace, providing each namespace with its own policy, access vector cache, and enforcing mode. And this data structure and the corresponding functions are modeled after the user namespace support that has existed in the kernel for some time. In addition to encapsulating the global SELinux state, it was also necessary to encapsulate the SELinux FS state as part of this work. This too was done by creating a new data structure, capturing that state, and then introducing support for multiple instances of the structure, including the ability to dynamically instantiate it on a per namespace basis. To support cases where one wishes to use the SELinux netlink socket in child namespaces, support was added to instantiate that netlink socket per network namespace, so that there could be separate netlink sockets for each namespace in which one is leveraging this functionality. The netlink implementation for SELinux was also adapted so that it would only send the policy load and set enforce messages to processes in the same network namespace, whereas previously it would have been sent always to the initial network namespace, potentially confusing the user space from a child. Support was also added so that if there's any case where one doesn't unshare the network namespace, we'll simply drop netlink notifications from child SELinux namespaces, which would otherwise have been delivered to the initial network namespace, protecting it against having its enforcing mode changed by activity in the child namespaces. In order to support per namespace process labeling, we extended the task security structure, which is SELinux's structure for per credential security blobs, to also include a pointer to the state structure representing the namespace, and a pointer to the parent credential in the parent namespace. This allows SELinux helper functions to be provided to find the appropriate label for a given namespace in order to leverage it, either for viewing or for performing permission checks. To support global SIDs, the existing SELinux SID table implementation was extended. The SID table implementation in SELinux already provided a way to maintain the mapping from SIDs to context strings due to the prior work to support deferred context mapping for cases where one actually sets a label on a file before one has loaded a policy module which defines the label. Wrapper functions were also provided for the secure server interfaces that provide this mapping. Currently, the global SIDs are mapped to the per policy SIDs in order to use the existing underlying security server functions, which still need to find the internal context structures that are policy specific. However, it would be possible as a future optimization to eliminate these per policy SIDs altogether and directly map the global SIDs to the per namespace context structures. To avoid imposing overhead on the case where one isn't using SELinux namespaces at all, the global SID table and mapping is compiled away entirely if the corresponding kernel configuration option is set to no. This is a screenshot of one of the helper functions that was introduced in order to support namespace permission checking. As seen here, we first obtain the appropriate security ID to use from the task's security blob and the appropriate state structure for its namespace. And then we obtain the target SID to use by looking up the SID of the target task that corresponds to that state or namespace. We can then perform our regular SELinux permission check using the access vector cache. Then, if there is a link to a parent credential, i.e. if this is happening in a child namespace, we can iterate up the credential structure link and continue checking until we reach the initial namespace. Of course, if there's only a single SELinux namespace on your system, then this will devolve to a single permission check as before. And of course, there's plenty of opportunity for our further optimization of this logic for the single namespace case. In order to support unsharing of SELinux namespaces, we implemented a new SELinux FS node, Unshare, which if you write a 1 to it, it will unshare your SELinux namespace. This was done primarily for ease of implementation. It could just as easily be a new flag for the clone and unshare system calls. However, one downside of adding a flag to the clone and unshare system calls is that one would either need per LSM flags, or all LSMs would be required to handle the unshare request at the same time, which could be quite complicated for differing LSMs. This unshare operation only unshares the SELinux namespace. The rest is left up to user space, which is responsible for unsharing the mount namespace, mounting a new SELinux FS instance, loading a policy, and setting enforcing mode. A convenience wrapper for unsharing the SELinux namespace is provided in libSELinux for use by container runtimes to abstract away from the SELinux FS-based interface. It's also possible to check whether one is in a non-init SELinux namespace by reading the unshare node in SELinux FS, which will return a 1 if the namespace has been unshared, otherwise a 0. This was primarily done simply as a convenience so that the SELinux test suite can detect whether it's running a child namespace and adapt its logic accordingly. It remains to be determined whether this would ultimately be suitable for upstreaming and exactly what it should return in different cases. For example, if it should reset back to being 0 again after a new namespace has been fully set up. A number of guardrails were included in the implementation to protect against misuse of the SELinux namespace functionality. First, the namespace functionality is not exposed to user space unless a new kernel configuration option, which defaults to no, is enabled. Second, a process can only write to its own namespace's SELinux FS instance. So even if it somehow obtained access to the SELinux FS associated with a different namespace, it would be unable to load a policy or change the enforcing mode of that other namespace, no matter what its permissions might be. The setting of the SELinux resource limits for the maximum number of total namespaces and the maximum depth can only be set using new SELinux permissions that were defined for these operations, along with the regular inode permission checks that are applied when accessing SELinux FS. They also can only be set, as previously mentioned, from the initial SELinux namespace, so they can't be later changed by any child namespaces. A further extension could be to allow child namespaces to make them only more restrictive than previously, but that's not currently supported. The interface for unsharing of SELinux namespaces likewise can only be set, and hence unshared, with a new SELinux permission that was introduced for this purpose, along with the corresponding inode permission checks to the unshare node itself. Further, the ability to unshare is limited by the resource limits that were previously set. Lastly, it should be noted that given that almost all the permission checks are checked against not only the current SELinux namespace, but all ancestor namespaces, the ability of a child namespace to, for example, create a file with a security label that might be considered sensitive or trusted by the host is constrained by the host's policy and thus can be prevented. In order to support experimentation with running real containers using SELinux namespaces, systemd nspawn and systemd were extended to support SELinux namespaces. This implementation is currently just a proof of concept in order to exercise the functionality, but ultimately, once the kernel functionality is accepted, we would look to upstream support, potentially in a very different form. First, we extended systemd nspawn by adding a new option to it to specify that it should create a separate SELinux namespace for the container. In this case, it calls the libSELinux convenience function during container setup to create a separate child namespace and unmount the old SELinux FS instance from it. This also sets an environment variable setting, which is conveyed to the init program launched by nspawn, so that it knows that it is operating in a child namespace. Alternatively, it could read the unshare node to detect that it's running with its own namespace if that interface is ultimately deemed upstreamable. Systemd then was extended so that if it's operating inside of a container and the environment variable is set, it calls the usual SELinux setup functions in order to mount a new SELinux FS, load a policy, and set enforcing mode. No change was required to that SELinux initialization logic. It all could simply operate as before. However, systemd did require modification because currently, if it detects it's running inside a container, it skips that processing since it assumes it shouldn't tamper with the host's policy. The policy of the container itself can be a stock distribution SELinux policy. You only need a local policy module added to that stock policy to deal with the new interactions between the container processes and the systemd nspawn instance, and any tempfs mounts it creates during container setup. Some of those extra allow rules in the local policy module can be further reduced or eliminated through further changes to systemd nspawn in order to properly label the socket it creates for receiving messages from the container and its tempfs mounts with labels that will be accessible from the container's policy already. The container's file system then is labeled based on its policy, not the host's policy. This can be done on first boot of the container if necessary, if the host's policy is completely different or doesn't allow the ability to set foreign labels. However, it could also be done from the host operating system or from the container build host, as long as the host's policy supports setting labels potentially unknown by its own policy. This is a screenshot showing a sequence of commands to manually create an SELinux namespace and initialize it. First, it cats the current value of the unshare node in SELinux FS, which is 0, because we are still operating in the initial SELinux namespace. Then it shows that we're operating with a unconfined SELinux context, and we're currently in enforcing mode in the initial namespace. It then echoes a 1 to the Unshare node in order to request unsharing of the SELinux namespace, followed by unsharing the mount namespace so that we can unmount the old SELinux FS instance and mount a new one specific to our child namespace. At this point, we can see by catting the unshare node that we are actually operating in an unshared namespace. And if we check our current process context, we can see it's been reset to simply the kernel value that's returned by SELinux when there's not yet any policy loaded and we're still operating in the initial SID. We also see that in the child namespace, we are currently permissive. The sequence of commands then proceeds to load a policy into the child namespace, run a shell in a particular unconfined context, and then switch to enforcing mode, at which point we can see we're now operating in that context and fully enforcing within the child namespace, which is independent of the parent, although still confined by it. This is a screenshot showing running systemd nspawn with the SELinux namespace option to spawn a container with its own SELinux namespace. As shown here, systemd nspawn creates a separate SELinux namespace and launches systemd, which proceeds to load a policy into the child namespace, perform its usual SELinux setup, and then boot into a Fedora container with SELinux enabled and enforcing. This slide has two screenshots. On the left is the output from a container running with its own SELinux namespace. As shown here, each process within the container is running with its own discrete security label as if it were running natively on an SELinux host. And as you can see, it's running in enforcing mode. On the right, we see the output of pstree-c running on the host of the same processes, where we can see that from the host point of view, all of the processes within the container are running with the security label from which systemd nspawn itself was executed. In order to test the functionality of SELinux namespaces, we ran the SELinux kernel test suite both in the initial SELinux namespace and in a child namespace. In the initial namespace, all of the tests pass as expected. In a child namespace, almost all of the tests pass currently, with the exception of a few labeled networking-related tests, which currently aren't namespace aware or supported. In order to run the test suite successfully in a child namespace, it's also necessary for the parent or initial namespace to allow all of the requisite accesses, which either requires loading the test policy into the host operating system policy as well, or otherwise making the host operating system permissive to avoid denying it when it's running in the child namespace. Patches for this are available in a branch of my SELinux test suite fork. Going beyond simply running the SELinux kernel test suite, we've also conducted some basic testing of booting SELinux enabled and enforcing containers on multiple different host operating systems and configurations. In particular, thus far, we have successfully tested Fedora, Rocky 8, and Rocky 9 in container operating systems, running on both Fedora and Ubuntu host operating systems, where the host operating system may either be enforcing its own policy or may have no SELinux policy loaded at all. To assess the performance overheads associated with SELinux namespaces, we ran a series of benchmarks on a set of kernels that showed different possible states. The baseline for the tests consists of a stock 615RC1 kernel plus what was the head of the SELinux dev branch at the time, but did not include any of the SELinux namespace patches. The no NS kernel configuration consists of the same kernel with the SELinux namespace patches applied, but the kernel configuration option set to no, thus showing any overhead associated with just enabling the underlying infrastructure, but not yet leveraging it for SELinux namespaces. The init.ns kernel consists of the same kernel source tree built with the configuration option enabled, but running the tests in the initial SELinux namespace, representing any overheads associated with the processing, but just within the host operating system itself. And then the child NS configuration consists of the same kernel, but running the tests in a child SELinux namespace to assess the overhead imposed on child namespaces. As shown here, this benchmark, the kernel compilation benchmark as packaged for Fedora, runs kernel compilations with different numbers of CPUs, and this was run 10 times with the results averaged and the standard deviation computed. As can be seen, the namespace support imposed no significant overheads, either in the initial SELinux namespace or in the child. We also ran the classical Apache benchmark using the SELinux namespace patches to assess any potential overheads associated with it, both on the networking and on the file system side. A subset of the results are shown here, but those not shown were similar. As seen here, the results for the namespace enabled kernels, both in the initial namespace and the child, showed no significant overheads and were within a standard deviation of the baseline. While there are a number of remaining open issues that ultimately need to be resolved in order to fully support SELinux namespaces at scale, the two listed here are the ones I believe are required prior to upstreaming the support to the mainline kernel. First, we need to finalize the kernel interface so that we don't upstream something that will ultimately break user space later. And so this really becomes a question of whether we simply stay with the current Unshare interface or add a new flag for the Unshare and clone system calls. As mentioned before, the complication associated with the latter is that it would either require per LSM flags or it would require all the LSMs to unshare simultaneously upon receiving the single call. And then secondly, we need to ensure that we've minimized overhead in the default case as much as possible. And while there's already been quite a bit of work to improve the performance situation, as shown in the results that I just presented, there's still potential areas where further improvements could be made. At this point, if I were there in person, I would turn to Paul and ask if there's anything else required prior to upstreaming this work. This slide lists other known open issues associated with the SELinux namespaces work. Each of these can be found with a longer description on the GitHub repo that is linked at the end of this slide deck. Some of these are focused on functional enhancements to the namespace support, such as the ability to support context-like mount options on a per namespace basis, or introducing label mapping support. Others deal with limitations of the current implementation, like the inability currently to fully namespace the network labeling capability, or namespacing of audit. Still others are more focused on functional enhancements, or even just validation, since we haven't yet actually tried to boot an Android container or a Ubuntu or Debian with SELinux enabled container using the support. With that, I'll end my presentation. I'd be happy to take any questions by email, either directly to me or to the mailing list. And the GitHub URL listed here provides both getting started instructions if you want to try out the support, as well as a list of open issues with fuller descriptions of what each one is, and possibly pointers to how to get going. Thank you, and enjoy the rest of the conference.